information, and that's the whole thing. So I guess a couple of most important points that we observed so far, and I guess the most important one is probably coming here on the part of the story with sequences, 9.1 section actually. So that's a little theorem that we saw already, but needs to be stressed again. So if you have a sequence which is monotonic, which means it just keeps going up higher and higher and higher. So we bound it by some particular number. So you can see from the picture, it looks like it keeps going higher and higher. So it's like having a horizontal asymptote analog. So our y coordinates of these points will end up with a limit somewhere in the area of L, because if you keep on adding more, you don't move down, you keep moving up higher and higher, and the highest is L, so it should be the limit L. And that's what they actually state here with sequences. Now, when you start adding things up, that becomes a series. So that's a little different. And that's what we're actually concerned with. The series produced when you start on adding numbers, more and more of them. And if we assume they all of the positive signs for convenience, because sometimes, yeah, it may be adding and subtracting, but if you keep on adding, if you keep on increasing your sum higher and higher, you end up with analog of the previous theorem, previous statement, when you have these terms, sum of one term, and then you keep on adding more and more positive values, so you keep on increasing. So if it is bounded by some kind of limit L, then this increasing or monotonic sequence should have a limit. And that limit is a sum of the series. So we're concerned whether we have a sum or not, and if it's monotonic and bounded, a sequence of partial sums, then it is convergent. In other words, it has a sum. And that's what they're discussing here in definition. So limit is sum of the series if the partial sum is convergent. So if you take sequence of partial sums convergent, then series is convergent. That deserves a little bit of a thinking. So over a weekend, it may be a good idea to think about this and enjoy it, because I guess that's the key portion of those sections. Now we also noticed there was a special kind of series, so you keep on adding, get series, such as geometric series. And those geometric series were produced by adding one term on the top of the other. So it's like, for example, where is geometric? Like one here. So you can just keep on adding more and more, and power and denominator is 2 to the n. So you get those pieces by multiplying by 1/2. If you keep multiplying by the same exact term, you get geometric. Like here, for example, you're multiplying by 7/6 or by 11/10. So they're all geometric series. But some of them will diverge in the case if your ratio is more than 1. Like here, ratio is 7/6, more than 1. So you keep on adding the terms bigger than 1, and the sum will be infinite. And same here, 11/10, more than 1, so you just keep on getting infinite sum. So they will converge if the ratio is less than 1. So if that's 5 or 6. And there is a theorem for that we saw, and that's good to realize. So geometric sequences, geometric series converge, and we even had a formula for their sum. So the formula for the sum we call this S, was first term divided by 1 minus R. And the key part is that R needs to be less than 1. And if you take it more than 0, and for the case of alternating series that we will discuss in, I believe, section 5 of this chapter, it'd be even easier. But for that case, they put absolute value, even though you don't need absolute value for everything we did so far. So you can find the sum of the series, just put R5 or 6 here in the formula, and you will even see what the actual sum is. Series converges, and again, the key point is that R is greater, less than 1, because if R is greater than 1, then series diverge. One can say, what happens if it's equal to 1? Well, then usually it is divergent, but again, it depends. So that's another part of the story that we went over. And then we also saw the case that the nth term needs to be approaching to 0, and then it's convergent. So that was a big deal to show if sequence series convergent or divergent. If it's convergent, then nth term approaching to 0, like we see here, nth term 5 over 6, so it's multiplied by 5 over 6, and again it gets smaller and smaller, so it approaches to 0, so it is convergent. Or if nth term does not approach to 0, it's greater than 1, then series is divergent. So that's so-called series test for diversions, basically. So if nth term is not approaching to 0, series is divergent. And then we saw very big deal, very special case for the so-called integral test that we discussed last time. So we shown, and here's the idea, if you remember, that the series and the integral, improper integral with infinity on the top, behave analogously. So they both either converge or diverge. And using that, we saw very useful in exercises case, so-called harmonic series that is divergent. So even though the nth term approaches to 0, but it is not convergent, and the way we shown it, we use the integral, and we ended up with ln when you integrate 1 over n or 1 over x as ln, and ln approaches to infinity. Now, in the analogous manner, we can also look at the theorem with different powers of n here. So if you have not just power of 1, but in general power of p. So what they show is if you have integral of n to the power of p, and when p is greater than 1, so if p is equal to 1, if power of n is 1, then it's divergent. But if p is greater than 1, then series is convergent. Now that's a big deal because it works for any power. For example, n squared. So the power is more than 1, convergent, or n cubed, or n to any whole power, it will be convergent. In general, it's p, which is greater than 1. So let's say if you take 1 over n to the power of 1 and little something, like 1.1, it's going to be conversion series. And you can show it by integrating. So if you try to integrate n to the power or x to the power of 1.1 with a negative sign, dx, dn, whatever. We usually use x, but anyways. So to take antiderivative, I will add 1, so I'll get negative 0.1 over negative 0.1, right? And this will go from like 1 to infinity, but instead of infinity, they put b. That's what we did last time, right? So we take a limit, and b goes to infinity. And notice that when you do this, you're going to end up with n in denominator. So that'd be n to the power of negative 0.1. And when you divide by 0.1, so that's going to be like negative 10, something like that, right? Flip that fraction. But the point of story that this is division of 1 by big, so it is small. So when n approaches to infinity, we get a result equal to 0. Right? So that's the idea. So whenever you have big number in denominator that approaches to infinity, the 1 over goes to small, so it's 0. And that's the big deal, because one may say that 1 over n then is a border, because once the power is more than 1, like 1.1 or 1.01 or 1.000000001, so just a little bit off 1, then right away the series is convergent when p is greater than 1, which is stated in the theorem above. And if you have the series with 1 over n, it is divergent. And for powers of n, it is true, but for the cases that are not powers of n, it is not true. Like, for example, they like to put n times ln of n, which is a little bit bigger than 1 over n, but it is also divergent. So it is not equivalent to some power of n, but this is a little bit greater than n, and that's, I guess, quite interesting to think about, because one may say, oh, 1 over n is a border, and the answer, it is not a border. That's the key point of this. And I think they even do it in the exercise here. So they use integrals. So they take integral test, they find antiderivative, which is here. So you can see it is going to be antiderivative with ln present, and it is still infinite. So it seemed to be straightforward when I'm saying this thing, but again, it's very good idea to give it a little bit of a thought. And a little bit of a thought telling you that no wonder why the textbook in the calculus is so huge. It's like 600 plus pages, because there's always special cases, sub cases. So you will have a hard time always to make a statement and that's it, and you're done. No, there are always counter examples and things, and that's one of the counter examples, for example, to the fact that 1 over n to the power of p is convergent. But anyways, we can, I guess, move on, because we were integrating a little bit last time. So now we want to try to, I guess, kind of summarize everything in terms of comparing series. For example, if you are going to look at the series in case 2, they both deal with 1 over n cube. And we know that 1 over n cube is convergent. And turns out the convergent is going to be also the series with 1 over n cube plus 1. And that plus 1, of course, makes it different a little bit, but it's still analogous to 1 over n cubed. And for that situation, they have a special theorem that will right away give you the, I guess, solution for tons of examples. So if that's a finite number, I think I need to maybe look at the actual statement of theorem here. So it's a big deal, really. It's a comparison test, so they say L. Let me clean my mess a little bit. Actually, yeah, I'm gonna stop share and share it again. Share it again. So if it's some finite number, L, then both series behave the same way. So if you have a series, sum of a_n's, and the other series is sum of b_n's, whatever a and b are doesn't matter. If the limit of the quotient of their corresponding terms is finite, like in the case where we had the example with a limit of one series was 1 over n squared, and the other was 1 over, no, it was n cubed, right? 1 over n cubed plus 1. So when n approaches to infinity, this limit ends up being 1, right? Because you can flip both and get n cubed plus 1 divided by n cubed. And this is a quotient of their leading coefficients. You can do 3 times derivative, but the point of story that you're going to get limit equal to 1, right? L'Hopital's rule, you can differentiate n cubed once, twice, third time, and same here, and you're going to have same thing on the top and the bottom and cancel everything, so you get 1. Or you could have divided by n cubed each piece of the top and the bottom. You'll right away see that's a leading coefficient of n cubed over leading coefficient of n cubed. So it is 1. So the point is, as long as it is finite value, let's say e positive, n positive. Well, positive will disregard the next section because we'll deal with positive and negatives. We wouldn't care. So for now, it is finite. So if it is finite, then series behave the same way. So if you know that the series 1 over n cubed is convergent, we just saw why. P series test because power is three for n, and it is greater than 1, so it is convergent. So if it is convergent, you can say as this series convergent, then series of this other type n cubed plus 1 is also convergent. So you're technically no longer going to care what's added, subtracted, whatever. So you know that dominating series is like a standard series, may not be dominated, but standard series, like 1 over n cubed or any p series, the power p for your n is more than 1. That's it, series conversion, and both of them will be conversion. And this helps tremendously to do the exercises. So if I go to the exercises, then right away I can declare conversion series for the number of those. So for example, take 19. This is analogous to the series, see, it's n squared n fifths, the leading coefficients. So it's 1 over n cubed, actually. 2/3, right? Leading coefficients, 2/3 over n cubed. So power of n is more than 1, then it is conversion. And you say, Alex, why didn't you look at the first one? Well, I'll look at the first one because this is equivalent to divergence series, 1 over n. So it's not just both of them going to be convergent, but if one is divergent and their quotient is fixed number, then the other is divergent. And we know that harmonic series 1 over n is divergent. So it looks like one needs to put on a piece of paper somewhere such a series as harmonic and know it's divergent, as well as p series, so one's power of p is greater than 1, then it'd be convergent. So how about this one? Well, this one is also divergent, right? Because this is analogous to 1 over square root from n squared or 1 over n. It is divergent series. So either convergent or divergent. So with all of those. Of course, if there is some other stuff involved, then you need to do a little more. But at this case, I'm just looking at all of the only power of n series, and looks like 26 is also going to be divergent because it's analog of 1 over n. Even though it's going to be 1 over 5 over n, and then it's also 5 over square root from n squared, which is another n, so it's going to be twice, but 5 halves, the constant make no difference because it's analogous to 1 over n. And again, you can use L'Hopital's rule to work this out. One can say, what about sine of 1 over n or tangent of 1 over n? Well, those are a little bit different. So those are ones that we already saw how to do using a calculator, graphing calculator, if you decide to graph function sine or function tangent and see what comes out. What comes out, of course, when n approaches to infinity, right? So that's, I think we already did it. You can try to do this again if you feel like. So these are not really having much to do with limits comparison, but this is still doable. I think I will get to those special cases after I'll finish discussing standard examples and what else is in the standard examples. So besides that limit comparison test, which is the key part of the story, there are some other things that we should always not disregard, because sometimes you cannot really use this limit comparison. Sometimes it's not clear what will be the series in a case if you have like arcsine or sine or whatever other functions that are not dealing with powers like 1 over n or 1 over n to the power of p. Well, then we use the idea of direct comparison. So what does that mean? Well, I guess the best thing is to take a look at the example 1. They already nicely put this down. So they say that this is convergent. Why is this convergent? Notice it's 1 over 3 to the power of n, but with a little bit extra, with 2 added. So that 2 will be disregarded because we have a convergent geometric series, 1/3 times 1/3 times 1/3, right? So that's geometric. You produce next terms by multiplying by 1/3. So ratio is 1/3, and ratio is, right, 1/3, which is less than 1, right? So we can get geometric series, and we actually get the sum of it by dividing a by 1 minus r. So whatever your a is, looks like when n is 1, it's 1/3, right? And you divide it by 1 minus r, and r is also 1/3, so you divide in 1/3 by 2/3, or you get 1 over 2. So you did not just show its convergent, you calculated its sum. So that's very powerful we have a formula, but we have it only for geometric series. That's pretty sad, but I guess it's better than nothing. So now what? Well, now what they notice is that 2 plus 3 to the power of n, when n is more than 1, is definitely greater than 3 to the power of n. Because of 2, right? So you add 2, so you make it bigger. And then when you take reciprocals on both sides, then the inequality will switch its direction. So when you divide by bigger, divide 1 by bigger, you get smaller than if you divide 1 by smaller. So that deserves to think about. So it's, again, they skip the step here, but now they say that this dominates. So this convergent which means that the smaller series will also be convergent. And of course, the reason is they are positive. So if you keep on adding numbers smaller together than 1 over 3 to the power of n, so the smaller numbers will give partial some monotonic sequence that will be bounded by that, and it's monotonic bounded, so it is convergent. So it's all going under the theorem, so it's a good idea to think about it. But you can find some other way to, I guess, write this down. Like, for example, you could look at that previous case, at the case when you have, again, let me write it down. So the limit when n approaches to infinity. So the test that we see in this section, an over bn. If it is going to be a finite limit, then both series behave the same way. So since this is convergent, then this will be convergent. Let's say why? Well, because when you take a limit of 1, which is 1 over 3 to the power of n, and divide by limit of the other, which is 1 over whatever denominator here is, 2 plus 3 to the power of n, it should be the finite number, right? Why is that the finite number? Well, take the limit. Notice they both have only one piece that varies. It's 3 to the power of n. So it looks like it should be the actual quotient of those 1 over 1, the leading coefficients. And how to put this better down? So I flip that one, it would be 2 plus 3 to the power of n, which is also divided by that 3 to the power of n. And I can divide by 3 to the power of n both pieces. And again, this is limit when n approaches to infinity. And notice that the first piece of this sum will be 0, right? Because fixed number over the infinite number. So this fraction approaches to 0. So I'm doing the same exercise, but different way. To show you it doesn't truly matter, since we have so many ways to find the conversions at this stage, well, then things become much nicer. So it's 0 plus 1, so it is 1. So technically, you didn't need to use this approach, which is, well, I guess, way more abstract. But you could use the following theorem. But one can say, how could I use that theorem if I didn't learn it yet? I learned it in the next page, right? So, well, the point of story, now you learned it, now you can use it in lots of exercises from previous sections as well. And that's the point of me talking about this. So this is really a very powerful result. But sometimes you cannot use it, so you need to use the algebraic approach, which is comparison test, which is not an obvious one. So this is for challenging exercises. But if an exercise could be done much nicer, then why bother? But they still show it to you to, I guess, demonstrate the case. And another example here for divergent series. So let me maybe clean this stuff out. So I'm going to stop share and share this again. And why is this going to be similar to divergent P series? Well, because the power is 1/2, right? So because power P needs to be bigger than 1. So it is conversion, but P is not bigger than 1. So you don't say it's bigger than 1, you cross it. It's not bigger than 1. So if it's bigger than 1, that power of n, then series converted, like n squared, n cubed. But if it is a square root of n, which is power of 1/2, which is less than 1, so it is divergent series. Again, take the antiderivative and see that you're going to end up with integral which is infinite. I think that'd be a good idea to try over weekend. So anyways, you could then say if you take a limit of corresponding n terms, and this will be dividing my terms of the series given 1/2 plus square root of n by a square root of n in denominator. Well, analogous little algebraic process. So we're gonna flip and end up with square root n over 2 plus square root n, right? Then limit will be, again, finite number. So these two series behave similarly. If one diverges like that one, so the other will be divergent. So notice, again, I'm not doing the exercise the way they do it here. I'm using the following test because that's really something that we need to always. So how can I divide that by 2 plus square root of n? No. Well, I guess I will divide by square root of n each piece of my numerator as well as each piece of my denominator, right? So this way my 2 over will disappear. It will go to 0 because 2 over big is small when n approaches to infinity. So this is 0. And then I will end up with 1 in numerator and 1 in denominator, right? So it'll be 1 over 1 or 0 plus 1, which is just 1. And the point of story, this is the whole number, the finite number, 1. And because of that fact, we have series behave in exact same way. So a comparison test says if L is finite, the limit is 1. In my case, then the both series either converge or diverge. So we have the idea. Well, anyways, what else could be added to this story? Well, there are some exercises that may be added like 27, 28. So I advise you to just graph 27 with a calculator so that way you will be able to see it right away. So if you go graph calculator here, graphing calculator. See, the great thing is we have that beautiful tool that costs over than $100, and whenever doubt, you can always use. Now you see, how can I put sine function here? Well, there are functions, right? So you can see there are lots of various functions that could be graphed. So sine, and then you want to use 1 over x, right? So it's going 1 over was 1 over n, but we can have 1 over x. So please notice that sine of 1 over x is definitely having an issue when x approaches to 0. There is no limit. But when x starts to be going to infinity, you just keep going to 0, right? Because if you want to zoom out, you can see it becomes really your x-axis. So sine of 1 over x, parentheses here to be nice. When x approaches to infinity, goes to 0. So the limit is 0, right? And what does that mean? Well, it means that series may be convergent. Let me go back to the series. So sine 1 over n is going to be approaching to 0. So how can I do the limit comparison test now? Well, I guess I need to think what this could be compared with, right? So is that 1 over n or what? So what should I do? But please notice this is going to be going to infinity. That's the key part. So you have a function. So there is some stuff happens, but then it keeps going to infinity, to 0, right? So that's the graph of my sine of 1 over x. But now we have not the sine of 1 over x, but what do we have? We have a summation from 1 to infinity. So if you put 1 over n, and n will start at 1 and go to infinity. So the question is, what about summation now? So yes, nth term goes to 0, but what happens with the summation? How does that gonna behave? But once again, if you try to use sine x over x, something like that, but it's going to be approaching to 1, but when x goes to 0, see, the point of story, this goes to 1, but when x goes to 0, but x does not go to 0. Does it? Well, or it does. When n goes to infinity, then we have 1 over x. When x goes to infinity, 1 over x goes to 0, isn't it? So it is actually comparable with sine of x over x, which is 1. So sine of this stuff behaves analogously to x, since limit when x goes to x goes to infinity, so 1 over x, so it looks like x goes to 0, right? So it behaves analogous to sine of x, sum of x's. So is this harmonic series or not? So that's what we looks like comparing it with. That deserves to think about over the weekend. You say, Alex, you told us to think about so many things over the weekend. I want to spend my weekend relaxing. Okay, think about it over next week. But the point of story, this is diversion. So that's what the point here. So this is going to be diversion. And you really think about the reciprocals. The one, because when x goes to 0, then it's somewhat 1 over x is divergent. And we end up with the limit equal to finite number. They both behave the same way. So if that's divergent, so this will be divergent. Follows from comparison. So this is something that, again, deals with comparison test plus the one in here I have. I say, Alex, how do you know that limit of sine x over x is 1? Well, first of all, that's a special first limit. I think we already discussed it before, but I know it's so easy to forget. Then, well, what can you do? Use L'Hopital's rule. Derivative of sine is cosine. Derivative of x is 1. So what happens with cosine when x goes to 0? It is 1. So that's why the whole thing is 1 over 1 is 1. So you can use L'Hopital's rule. See, now we learned a few very powerful things, such as L'Hopital's rule that deals with pretty much any limit, as long as it's 0 over 0 or infinity over infinity. In our case, it's 0 over 0. So take derivatives and you get that fact right away. You don't need to remember anything. And now we also have the other property, the one that I think is another extremely powerful for the exercises theorem, again, the comparison of the limit test. Because otherwise the problem we have here would be much longer. You would need to do this, compare with some other things, and it's easier just to use this 9/13 theorem. So I guess at this stage is a good moment to stop, to give you a break, to have you relax and enjoy the weekend. So next time we will look at very interesting section when we have sine alternating series, and it's interesting. So some with pluses, minuses, so some terms will compensate each other. But there'll be just amazing result. The amazing result, probably the most amazing result you see in the course of calculus. So that's the one you should get morally ready. That's why I want you to relax very well, because some people might get really amazed when they see it next Tuesday. So I'm going to stop.